We'll start our last lecture of the day, and I also want to remind you that at the end there will be a reception outside at 6 o'clock. So it's a great pleasure to introduce Laszlo Lovász from, I have been trained at Loránd University from Budapest, and it's a great pleasure. So the title is Large Graphs and Graph Limits. Please.
Thank you very much, and thanks for IMPA and Marcelo for this invitation. I've been here several times before, and it has always been a great pleasure. It has been a little while now that again I'm here, so I'm really very glad. I will talk about the topic. I will start actually with the second part of the title about graph limits, what they are and why are they interesting at all. And then I will show a couple of applications of this graph limit theory to large graphs, so to the first half of the title. So why are they needed? Let me start with a very classical high school or maybe first year college problem. Let's try to find the minimum of x cubed minus 6x over non-negative x's. And you probably already see that the minimum is attained at square root of 2. So in particular, the minimum is not attained in rationals. So if you only believe in rational numbers, then you can say that this minimum is not attained. Or maybe you are a believer in Greek philosophy of mathematics. But so you could say that, well, this minimum is not attained, but you can get arbitrarily close if you allow large enough numerators and denominators and so on. But anyway, it's convenient to talk about the minimum as a single number instead of an equivalence class of Cauchy sequences. And so we know that real numbers are useful. Now let's look at an optimization problem in graph theory. So suppose you have a graph with edge density half, so half of all possible edges are present, the other half are not. And you count 4 cycles in them, so say maybe repetition allowed, so how many ways can you make 4 steps and get back to the point where you started? And you want to find a graph which minimizes this number. And then there is a theorem which says that this number is always larger than 1 over 16. I don't know, theorem in this form, I mean, the argument itself occurs first probably in the work of Paul Erdős from the 40s or 30s, late 30s, so it's an old thing. And that it's always strictly larger than 1 over 16. But it gets arbitrarily close if you, for example, construct a random graph. So you take n points and you construct a graph by flipping a coin for every pair of points, and if it comes out head, you connect them. If it comes out tails, you don't. An equivalent way of saying it is that you think of all graphs on a given n points, you put them in a big bag, and you randomly pull out one. And then with large probability, the edge density will be 1/2, and with large probability, the cycle, or very close to 1/2, and with large probability, the density of 4 cycles will be very close to 1 over 16. These are easy computations, and the larger n is, these numbers get closer and closer to this target. So it's similar a situation that it's some minimization problem where the optimum is not attained, but we can approximate it arbitrarily well. It's not attained among graphs, and that's why one of the reasons why graph limits are useful. So we would like to construct the analog of real numbers, but this time not for numbers, but for graphs. So how to what is the completion of the space of all finite graphs? So let me introduce some pictures here. If we start with a graph, I mean, that's a traditional way of drawing a graph. You draw some nodes and you draw edges that collect that nodes. If the graph has more than 20 nodes, you don't really see much from such a picture. You can also construct the adjacency matrix of the graph. This is very useful in computations, but I'm sure that from the back of the room you cannot really read it or see anything in it. I'll only do a little change to this. I replaced every 0 by a little white square and every 1 by a little black square. At least you see it better what's going on. We get this kind of picture which looks like a crossword puzzle. Now, the way I consider this is that this is the unit square. The whole area is the unit square, and so it's divided into n squared little squares. And where you see white, it means that the value is 0, and where you see black, it means the value is 1. So this is a function on the unit square with values 0 and 1. And another remark that because it comes from a matrix, we put the origin to the upper left corner. Okay, so this way, to every graph, I associate this picture, which I will think about as a function in two variables defined on the unit square, and with values 0 and 1. We talked about random graphs, so here is a function that it was obtained as just a random graph with 100 nodes and half of the edges present. And this, depending on the projector, it looks more or less similar to the simple gray, all gray square on the right-hand side. So in fact, random graphs are sort of gray. There's no feature. But you have to be a bit careful, and okay, here, let me give you another example here. So we want to say that if instead of this 100 we take a large, very large number n of nodes, and n tends to infinity, then these random graphs tend to this gray picture, which I am thinking of as the identically 1/2 function on the unit square. So the limit of random graphs should be the identically 1/2 function. Here is another example. This is another somewhat maybe more structured, a lot more structured class of graphs called half graphs. These are bipartite. They have two classes of nodes, and all the edges lean to the right. And every pair is connected if the corresponding edge leans to the right. The corresponding pixel picture looks like this, and it doesn't take much thinking or figuring out what should be the limit of this sequence of graphs. Clearly, it should tend to this function, which is again considered as a function on the unit square, and I think in this case I forgot to rotate it, so sorry about that. So the origin is now in the lower left corner, but so it's a function. It's a two-variable function. It's 1 on those two triangles and 0 elsewhere. So here is a random graph tending to the identically 1/2 function. Now, where should this picture tend to? So this is like a chessboard. Of course, there's some corresponding graph. And of course, one thinks that it should tend to the identically 1/2 function again. In fact, as a picture, it would tend to the identically 1/2 function. But that's an important difference between image processing and this theory, that we don't really have an order on these rows and columns. And actually, the real name of the game is to find the right order. So to find an order where the convergence feature comes out. So as a matter of fact, here we can rearrange the rows and columns, just start with the even ones and then put the odd ones later, and then you get this picture. And in fact, in this case, it's obvious what is the limit, because for whatever n is, you always get this picture, so this picture should be the limit. So let's see a little bit more complicated example. This is a graph which is called the uniform attachment graph on 200 nodes. The exact rule doesn't matter too much, but so the idea is that we are creating a graph step by step, and at each step we either create a new node or we create a new edge. A new node is just a new node. If we create a new edge, then we just put it anywhere uniformly. So for any pair which was not connected. And you have to adjust the rate of creating nodes and edges so that eventually the density comes out, say in this case, 1/2. That's how I adjusted it. So this is a randomly grown uniform attachment graph on 200 nodes. And if you look at it from a distance, and if the project comes out all right, reasonably all right, it will be similar to this function, which is a very simple function, is 1 minus the maximum of x and y. So, in some sense, this randomly growing, very complicated graph should tend to this simple function. Okay, well, it's believable that it tends to this function. Now, what is good for it? In what sense should it tend to this function, and what is this knowing this limit good for? Let me start with this question. So, what is it good for to know this limit? What information does it contain about the graph? It turns out that it contains a lot of information about the graph, and there are many properties of this graph which can be recovered once you know the limit. I will only give a very simple example. So suppose you want to know, say, the triangle density in the graph. I could say, again, 4-cycle density or something. So triangle density means what is the probability that if you start at a random point and you make 3 steps, you get back to where you were. So what is the... Or you pick out 3 points. Let me put it like this. You pick out 3 points. What is the probability that you see a triangle? That's the definition of the triangle density. So you can ask this about this graph, and you can struggle long with recursions and so on to try to figure out what this density is. But if you know the limit, then there's a natural formula for that. You will see that we assign a variable to each node of the triangle, so there will be 3 variables. And then for every edge of the triangle, we integrate this limit. It's a 2-variable function. We put in this limit, we take this product, we integrate it. It's a very simple thing to see that this really is what you would like to have the triangle density. And so we would like to show that this limit, indeed, in this sense, reflects an interesting object that somehow reflects a good number of properties of this sequence. So let me now give you a little bit of the math of this limit theory. So I denote by TFG the probability that if you take a random map from the vertex set of F to the vertex set of G, then all the edges are preserved. So this is kind of the density of F in G. If it's a triangle, then you get exactly the triangle density. Now, it's a definition. We say that a sequence of graphs, growing larger and larger graphs, is convergent if the density of every fixed graph f has a limit, tends to a limit. So the edge density has a limit, the triangle density has a limit, and so on. For every fixed f, this has a limit. Now, okay, so those special, very special graph sequences that I have shown you before are convergent in this sense. So if you take larger and larger random graphs with the same edge probability, it is convergent with probability 1. The half graphs form convergent sequence, and so on. Now, if we talk about convergence, we have to somehow describe the limits, and the limits can be described by, we have seen this already. These are two variable functions, symmetric measurable functions, defined on the unit square and with values between 0 and 1. So somehow we call these graphons, these kind of functions. So these represent the limits of graphs, or in other words, the completion of the space of graphs. And again, this is a formula which generalizes what we have already seen for triangles, that the density, you can define the density of a graph f in a graphon W by this integral. So you have a variable for each node of f. You have then a wxy, a factor for each edge of f. You take the product of these and you integrate. And so we say that a sequence Gn tends to this graphon W, so this is what we have seen examples of, if for every f, the density of f in Gn tends to dfw. So it's convergent if this density tends to something, and W represents these limiting values. Okay, so this is a definition. And let me stop here for a second. It's clear that every sequence has a convergent subsequence, because you can just do this by diagonalization. You pick a sequence for which the edge density converges, subsequence. You go to a subsequence for which a triangle density converges, and so on, and then you take the diagonal, and then everything will converge. So there is some compactness here in the background. Here are somehow two of the theorems that are important here. So first of all, for every convergent sequence, the limit can be represented by a two-variable symmetric measurable function W, by a graphon W. Now, you may think that this is somehow too general. I mean, measurable functions are a rather general class, and graphs are very simple finite objects. So maybe it's an overkill to use such complicated objects to represent these limits. However, it is not an overkill, and the other two statements tell this. So first of all, if you take any such graphon W, then it's easy to construct a sequence of graphs, reasonably easy, which will converge to it. So every such W is the limit of some convergent graph sequence. And you could still say that, yeah, but there may be several W's which represent the same limit. And indeed, there will be several W's representing the same limit. You can replace each variable by 1 minus this variable, for example, and more generally, you can apply any measure-preserving map in each variable, and this will not change these integrals, so it follows that. So you can apply any measure-preserving map, and it turns out that that's all. So this W is really unique up to this kind of transformations. I'm not stating this theorem exactly, but that's the essentially. So indeed, it's interesting that graphs which are simple finite objects, to represent their limits, you need all measurable functions, and it's exactly that into variables. Now, okay, so let me show you two applications of this theory. The first one is in extremal graphs theory. And let me give you a little introduction into extremal graphs theory. There is the classical theorem is Turan's theorem. That's usually the beginning of every course on this subject. Actually, I'm only quoting a special case which was proved more than 100 years ago by Mantel. And it says that if you have a graph that contains no triangles, then the number of edges is at most, n is always the number of nodes, and m usually is the number of edges. So the number of edges is bounded by the square of the number of nodes divided by 4. I mean, n choose 2 is a trivial bound, so this is about half of the trivial bound. And equality holds if it can, so if n is even, then you just split the nodes into two equal classes and put in all edges between the two classes, and then equality holds. So it's a very simple classical theorem. There is a stronger theorem here which says that let's not just talk about whether there is a triangle or not, but let's estimate the number of triangles. And it gives a formula for this. The point is that there is this 4m over n squared minus 1. Now, if m is less than n squared over 4, then that's negative, so the whole inequality is completely trivial. So it gives a negative lower bound. But once that number is larger than 1, the lower bound is positive, so the Mantel-Turan theorem follows. Okay. So let me quote another old theorem. It's the Kruskal-Katona theorem. Again, a very, very, very special case. It gives an inequality in the opposite direction. So I tell you the number of edges, how many triangles can the graph at most have. And, well, the one way to remember it, there are many ways of stating it, is that if you write the number of edges in the form k choose 2, k is not necessarily an integer, then the number of triangles is bounded by k choose 3. And if k is an integer, then you actually have equality for some graph, and the graph is very simple. You take a complete graph on k nodes, connect everything, and you throw in the other nodes without connecting them to anything, as many as you wish. So this is the Kruskal-Katona theorem. And, okay, so the question is, what can we say in general about the relationship between the number of edges and number of triangles in a graph? So the previous two theorems were rather simple classical theorems taught in every course on the subject, or many courses in the subject. But let's try to be more complete. So what this picture says is that I take the horizontal axis is the edge density, and the vertical axis is the triangle density. Every graph will give me a point here, so think of it as a little red point there. So if I plot it for every graph, I get some subset of the unit square. Well, it's a countable subset, but let's take the closure so that we could describe it easier. So, and it will turn out that the closure looks like this. If you look at, so I have shown, okay, some special values will be important, but we'll see it in a minute. So first, let's look at the upper curve. It turns out that this is the Kruskal-Katona theorem, and that's the x to the 3 halves. So if you translate that into into this normalization, then you get the x to the 3 half. And this curve, I mean, most points on this curve are actually not attained because they are irrational, or maybe even the rational points on this curve are not attained because maybe some number theory intervenes. But you get points arbitrarily close to every point of this curve. So the closure will, the boundary of the closure is this curve. Now let's look at the other half of the picture. So first of all, the Montel-Tuan theorem says that above 1/2, the curve leaves the x-axis and goes up. I mean the lower boundary. Up to 1/2, of course, you need not have any triangle, because with 1/2 we have seen this graph with two complete bipartite graph, and the subgraphs of it fill the line up to 1/2. But above 1/2 it has to be larger than 0. And the Goodman theorem that I also quoted tells you that actually everything is above this parabola that goes through these 3 special points. Now you can ask whether this is attained, and indeed there is an infinite set of values where it is attained. For edge density 1/2, it's the complete bipartite graph. For edge density 2/3, it's a 3-partite. You do this the same thing, except you split the points into 3 parts, and then the next red square there corresponds to splitting the points into 4 equal parts, and so on. Now, what happens in between? The first guess would be that it's similar to the Kruskal-Katona thing, so maybe some number theory stands in the way, but that you cannot reach exactly this parabola, but you will get arbitrarily close to this parabola. It was a big surprise when Béla Bolobás proved, we are now in the 70s, mid-70s, that that's not the case. In fact, if you take 2 of these special red points, you connect them by a chord, then actually every valid point must be above this chord. So the points on the parabola that goes strictly below the chord are not approximable by, so they are not really limit points. And then the question is, what happens actually? Is the chord the truth, or is it above? With Miki Simonovic, actually, in the same conference proceedings where Béla published, we also published a conjecture that actually described this curve. It was some cubic curve. It's an ugly formula, but anyway, there was some justification, and we proved it in a little interval above 1/2, but so on. And then Fisher proved our conjecture in the first interval. So it's a concave curve, a concave cubic curve, which is the border there. And quite recently, Razborov was able to prove the conjecture for the whole line. And then it's not hard to see that that's all, so you don't get any other tricks like maybe missing islands in the middle or something like that. So it's really, if you plot edges versus triangles, you get exactly this area bounded by this countable number of cubic curves. So one thing is that it's a very simple problem, simplest possible question you can ask about counting things in a graph, and the answer is quite tricky and difficult, and Razborov's proof is a real difficult, complicated proof. He uses actually, and I must say that he uses limit theory for graphs, which he developed independently partly for the purposes of this proof. And one can show that the 2 theories are equivalent. He puts things differently than I did, but it's equivalent. So this is about this picture, and I will come back briefly to this picture a bit later. Now, let me introduce some convenient formalism here. So there is Goodman's theorem, now stated in terms of densities. So recall that tk3g is the density of triangles in G, and I just rewrote his theorem in terms of these densities. So it's this quadratic inequality. Now, it's not convenient to have all these lots of t's and everything around, so I just took out what changes. And so there's a triangle minus twice the edges, but it's squared, plus once the edge. Now, you may say I'm cheating here because now what is it? Is these two edges that I have drawn here, does it mean a graph consisting of two edges or two graphs each consisting of one edge? Well, it turns out it doesn't matter because the density of two disjoint edges is just the square of the density of one edge. Remember, it's a probability that if we randomly map, then edges are preserved, and since the two edges there's no edge between them, the two components, so the these events are independent. So you can sort of think of it as the product of an edge with itself. Just write it down. I could write square even. And the Kruskal-Cotonut theorem also has a very nice formulation in this sense. It's two disjoint triangles are better than three disjoint edges. That's what it says. So I will talk about linear combinations of graphs here, and that it is non-negative, meaning that this corresponding inequality holds for every G. Now it turns out that the Bolobar theorem I quoted, which is actually more general, and it was a little bit further generalized by Schelp and Thomason, what it tells you is the following, that if X is a very special kind of graph, it's just a linear combination of complete graphs, so talking about maybe edge density minus 3 times the triangle density plus 50 times the density of 5 cycles, something like that. Some kind of linear combination like this. Then there is a simple criterion to decide whether it holds. It holds for every graph G, if and only if it holds in every complete graph. That's actually a fairly surprising result which has far-reaching consequences. So, for example, the fact that everything is above these chords, if you recall, follows because this chord, the line of this chord represents a linear inequality between edge density and triangle density. Complete graphs are exactly those special red points for these two parameters, and therefore it follows that since this line respects all the red points, everything is above them, all the other points are also above them. So it's a highly non-trivial theorem, and it's very nice because what it tells you, you can translate it into arithmetic, and it says that a linear inequality between densities of various complete graphs, edge density, triangle density, complete 5 graph density, and so on. Such an inequality holds if and only if this kind of very simple algebraic inequality holds, and in particular, there's a first-year calculus exercise to show that such an inequality can be actually decided. So one thing it follows that for this kind of questions, linear combinations of complete graph densities, such a problem is decidable. I mean, it's much more. It's a polynomial time decidable. It's easily decidable, and so on. So this raises, of course, the question: is it really important that this is a linear combination of complete graph densities, or maybe you can generalize it to other inequalities? Quantum graph is just a formal linear combination of graphs. So what the question means, suppose you come to me and say, I suspect that 5 times the edge density minus 13 times the triangle density plus 45 times the density of 5 cycles plus 17 times the density of Petersen graphs is always non-negative in every graph. And now I am supposed to answer you yes or no. Is it true or is it not true? And so remember, for complete graphs, we can do it. Now this is actually, there's a lot of analogy here with the theory of non-negative multivariate polynomials. So if you have a non-negative, say real polynomial, or maybe, let's say rational coefficients, just to be able to handle it algorithmically, and you can ask whether it's non-negative for every substitution. Well, we know, I mean, that's Hilbert's 117th problem, I think, and whether such, is it true that every such polynomial is the sum of squares of rational functions? I mean, the first question is whether every such polynomial is the sum of squares of polynomials, and we know that that's not true. So Hilbert knew that this was not true, so he asked whether it's the sum of square of rational functions, and that's Artin proved that this is true. From this it follows, and it also follows from some more general theorem of Tarski, that this question is decidable. So if you come to me with a particular polynomial in n variables with rational coefficients, and you ask if this is non-negative for every substitution, then I have an algorithm to decide this. There's an algorithm. It's not very efficient, but there is an algorithm to decide this. On the other hand, you can come and ask, is it non-negative for every integral substitution? And it turns out that this is undecidable. That's Matiasevich's famous theorem. So multivariate polynomials give examples for decidable and non-decidable. And the question is, what about this graph theoretic problem? Well, it's a beautiful theorem of Hatami and Norin, which says that it's undecidable. So it's more similar to the integral substitution of polynomials. So there's no algorithm to decide whether a linear inequality between subgraph densities is valid for all graphs or not. Now the Hatami-Norin proof is very, very, very pretty, and it connects nicely to our to what I said before. So the point is, of course, you take a polynomial which you want to know whether it's non-negative for every integral substitution, and then you somehow construct a multivariate polynomial, construct a graph, a linear combination of graphs, somehow encode it as a linear combination of graphs, and then if you could decide that that is non-negative, you could decide this is non-negative. And here is the main trick of the proof. It's relatively easy to encode it as subgraph densities. But then the problem is that then you reduce it to the real substitution case, and that's decidable. So the question is, how do you force these subgraph densities to be, I mean, you cannot force them to be integral because they are numbers between 0 and 1, but it turns out you can force them to be in this special sequence 1/2, 2/3, 3/4, and so on. And how do you force it? Well, you write up Goodman's theorem, density of, and you say there should be equality there. And then by Bolobash's theorem, this equality happens only in those special points. So now you force this variable to be of this special kind, and now it's just a matter of a tricky algebraic transformation to map these into integers, and now and then you have to construct a tricky graph, and this way you reduce the problem of deciding a polynomial whether it's non-negative for every integral substitution to the question whether this kind of typical extremal graph theory inequality holds. So this is a very nice result. So it is undecidable. A little bit of a positive thing is that it's decidable with an arbitrarily small error. So if you specify, is this linear combination? Well, I mean, if it's maybe not always non-negative, but maybe I allow you to get that it should not be really less than one in a million, then this is already decidable. Well, I mean, that's a theorem, but it is decidable. Okay, so why is it decidable? Let's come back to computing with graphs. So, I mean, we have seen that we take linear combinations of graphs, and then we also take this, which I call the product of disjoint union. Now, this is not, we have to be a little bit more tricky of this, about this, and we consider k-labeled graphs. A k-labeled graph is a graph which has some k special nodes, which are labeled 1 through k. It can have any number of unlabeled nodes. And we think of these labeled nodes as kind of terminal nodes which it communicates with the outside, and the others are. And now if we have two k-labeled graphs, then I define their product as taking the disjoint union, but identify the labeled nodes. So just glue them together along the labeled nodes. And then we can extend this to these formal linear combinations just linearly. So let's do a little bit of a computation. So this, now when I write a dark point, that should mean it's labeled. So now I have here a linear combination of 4 labeled graphs, each of them having 3 labeled nodes and no unlabeled nodes. And let's take the square. If you work it out, actually, this is a very nice combination because it's idempotent. The square of it is itself. It's a simple computation. The other thing is not so nice. I take another linear combination there. This time, these are 1 labeled graphs. So they have 1 labeled nodes and 2 unlabeled nodes. Take the difference of them, square it. It's just the edges put differently. And you get some junk, some linear combination of things on the other side. Actually, I think I forgot to put a 2 in front. I mean, this is twice that, because I want to add these guys up. So I take the first square plus twice the second square. I get some junk, lots of the combination of these graphs. But let's do 2 things. First of all, I forget now the labels. The labels did their job. They can go. So I forget the labels. And also, I don't care about isolated nodes. Say the last one has a node which is not connected to everything. I delete those 2. So I get, what I'm left with is this expression. And this may be familiar to you. A triangle minus twice a double edge plus once the edge. That's exactly the Goodman combination. So Goodman's theorem said that this was non-negative. So the densities in every graph with this, combined with these coefficients, is non-negative. And you can say, now, of course it's non-negative. It's a sum of squares. So this is a proof of the Goodman's theorem, isn't it? It is actually. Okay, so this is the meaning of it in more explicit terms. Just Goodman's theorem. So it is not hard to prove that if a quantum graph, so it's a formal linear combination of graphs, is the sum of squares in this sense. So you first have labeled nodes, you square certain expressions, then you take a linear combination and forget about the labels, and delete isolated nodes, then this is non-negative. So this is good. So that's not hard to verify. It's just some simple Cauchy-Schwarz inequalities and various subgraph densities. And now, of course, you can raise the converse. Suppose that x is non-negative. Does it follow that it's a sum of squares in this sense? Well, it turns out that the Hata-Minorin theorem almost immediately tells you that this cannot be true. Because if it were a sum of squares, that would mean that there is a finite proof that it's always non-negative. Of course, there is also a finite proof if it's not non-negative. So if there is a graph in which the density the inequality is not satisfied, because that graph is finite, so it's just specifying that graph is a finite proof for the opposite. So you could just construct two Turing machines. One was looking for writing it as a sum of squares. The other one was looking for an appropriate graph G. One of them wins, and so that's a decision algorithm. And since there is no decision algorithm, it follows that this cannot be true. You have to be a bit careful with the coefficients being algebraic and so on, but all this is easy to straighten out. Since you cannot prove all valid inequalities by any means. On the other hand, one can prove, and that may be interesting, that it's non-negative if and only if it is in the closure of square sums. I have not defined the topology, so I will not exactly tell you what closure means. It's a natural, you can define an L1 metric, and it will be the closure of this. So it's almost true. It's close to being true. Okay, so let me briefly talk about another application as another different area. This is computer science, and it's called property testing in computer science. So the graph is, so suppose you have a graph which is huge. Think of billions of nodes. And it's not known, it's hopeless to know it explicitly. Think of the internet. I mean, you will never be able to map exactly the whole internet. It will always be sort of fuzzy parts. So think of such a graph. And so we would like to define, say, algorithms and other problems for such graphs, say algorithms for such graphs. Now we idealize, we define the minimum amount of information from which anything meaningful can be obtained. And one possible model is the following. It's about 20 years old, or maybe a little more. It goes back to the work of Goldreich, Goldwasser, and Ron. And what it says is that here is the hypothesis or the model. We can sample uniformly a random node. So even though we don't know all the nodes, somehow we have access enough so that we can pick a node. Now it's a node, you don't see much from a node, but you can repeat this a bounded number of times and you will have maybe 100 nodes, and you see the edges. The assumption is now you see the edges between these nodes. So you see a random subgraph induced by these 100 nodes. That's the information you get. And the question is, what can you conclude about the graph? So it's like statistics. You pick a random sample, but it's not about numbers, it's a statistics about graphs. And now I will assume that the graphs that I consider are dense, so they contain a constant fraction of the edges. Otherwise, the whole model doesn't make much sense. Now, this relates nicely to the notion of convergence, because it is not hard to see that a sequence of graphs is convergent in the sense I defined earlier, if and only if you fix an R and you take a sample that gives you a distribution on graphs with R nodes, and if these distributions are getting closer and closer. So in other words, if you have a convergent graph sequence, then by sampling you cannot really distinguish two graphs which are late in this sequence. So anything that you can compute, say a parameter from sampling, it better be convergent for a convergent graph sequence. So for example, if here is actually, to show that this question can be quite tricky, here is an example. Is the graph triangle free? So it's a question. So, well, first of all, and there's really not much you can do. You can take a sample. If you see a triangle in that sample, then you conclude that the graph is not triangle free, and that's it. What happens if it contains no triangle? Well, the only thing you can conclude is that the original big graph cannot contain too many triangles. It will contain a negligible fraction of all triangles, because if it contains a good fraction of all triangles, then the random sample will pick out one of those. So it contains a very small fraction of triangles, and if you replace the 100 by 1,000,000, then it will contain a much smaller fraction of triangles with large probability. But this is all statistics, so I may forget to say this high probability thing. Now here is what the model says. We would like to conclude from this that the graph is close to being triangle free, which means that we can delete a small fraction of the edges and destroy all the triangles. This looks like a completely innocent statement. There's a few triangles, so why couldn't we destroy them by a small number of edges? But remember, the number of triangles it's a small fraction compared to n cubed, so the density is small. So that there's still n cubed triangles. If you delete one edge from each of those, you may be deleting all the edges. So this is actually a very deep theorem. It's called the Ruzha-Semeredi removal lemma. And it's one of those really annoying points where you first hear it, you say, oh, okay, I mean, I'll do it by the end of the talk. And then it turns out that it's actually a quite difficult statement. It uses the regularity lemma of Semeredi, and people have worked very hard on trying to improve this. And in fact, there's too small. I mean, there's a few triangles and a small number of edges. So this is an epsilon 1 and an epsilon 2. And you can ask, what is the relationship between epsilon 1 and epsilon 2? And it turns out that epsilon 1 should be something like 1 over 2 to the 2 to the 2 to the 2 to the 1 over epsilon 1 times. So it's an unbelievably small number. So the number of triangles must be unbelievably small fraction of all possible triangles in order to get anything decent about the number of edges to be removed. There is no proof that you really need it this bad. I think there are examples that it's exponential, but not this tower behavior. Actually, I said a tower of 1 over epsilon. There's a very recent improvement by Fox, which improves it, a tower of log of 1 over epsilon, of height log of 1 over epsilon, which is still a tower. It's still extremely high. So anyway, so property testing for this very simple property is actually quite an interesting and tricky business. So here is now the definition. We call a graph property testable if there is another property, which we call the test property T, so that if we have a large enough graph, then this graph has the property, if the graph has the property, then a random induced subgraph of it has the property with probability 2/3, say, at least. And if it is far from the property, meaning you have to change many edges to change it, to restore the property, then this random induced subgraph, the sample you take, has this property with probability less than 1/3. And 2/3 and 1/3 could be just any numbers larger than 1/2 and less than 1/2. So this is the standard notion of testable property. And it turns out that, I'm almost done, there are some very beautiful examples of testable properties. I have shown you one, which was triangle free. There's a much more general theorem due to Allen and Shapira. It says that every hereditary graph property means that if a graph has the property, then every induced subgraph of it has the property. So triangle free is a trivial example. If the big graph is triangle free, then the small graph is triangle free. Actually, that's why we could use the same property for testing on the small graph and big graph. So every such property is testable. Now, there is a tricky notion which is non-deterministically testable, except if you are a computer scientist, then this is really your bread and butter to turn everything in, look at the non-deterministic version of everything. And non-deterministic means that there is a certificate that if you have this certificate, then it's easy to verify that this certificate is correct. The usual thing is that if you want to know that a number is not a prime, then a certificate is a divisor of the number. It's not so easy to decide whether the number is a prime, but if I tell you the divisor, then it's very easy to check that it's indeed a divisor. So a divisor is a certificate that the number is not a prime. And it could happen for every graph property that sometimes it has easy certificates. So for example, in this case, the certificate is a coloring of the edges of the nodes, and we say that it's a certificate for this property if, together with this coloring, it's easy to check that indeed that holds. So let me give an example. So suppose that the property is that this graph contains a cut, so you can split the points into two classes, so that there are many edges in between, say at least n squared over 10 edges going across. So why is it non-deterministically easy to test? Well, you know, this superior being comes and takes two colors and colors the two sides of the cut with red and blue. And now you only have to statistically test how many edges go across, and that's trivial statistics. You just pick a number of points and count how many edges go in between. So if he gives you the right cut, the right coloring, then it's very easy to check that it indeed has this property. So the point is that on the other hand, otherwise it's not clear what to do. And so there is a recent theorem of Coty and myself. We proved that if it's non-deterministically testable, then it is also deterministically testable, which is somehow not really intuitive. In fact, for the computer scientist, it really says that P equals NP in this setting, in the setting of property testing. Now the question is, what does this have to do with graph limits? And I mean, I will conclude just with this picture. So what would it mean that it's not testable? It means that there is first of that you will have two sequences of graphs which are difficult to distinguish from each other, and one sequence has the property and the other sequence is far from having this property. You have to change many edges to restore this property. Now, and nevertheless, the Gn here is close to Gn prime. Now I told you every sequence has a convergent subsequence. We can go to this subsequence, this converges, that converges, and from the fact that these two are close, it implies that they converge to the same. And so there is this kind of magical function in the middle. Now these are in the properties, so for these graphs you can define appropriate colorings, which are easy to test. You take these colorings. It turns out that they go up to this limit. They can be add that structure to the limit. And then there is a more harder argument which shows that from the limit you can pull it down to the other side. And so it follows that they also will have certificates, so they cannot be far from the property. So this is just a very rough description of this. And I conclude with the very negative fact that this is a pure existence proof for an algorithm, which almost seems like a self-contradictory statement. So it says that there is an algorithm, a testing method to test this property, but since we go through this limit, there's no way, I don't see any way to make it finite. There may be a way. Noga alone tells me that using some strong versions of the regularity lemma, he can actually probably make it, but it's not written, make it constructive. So anyway, if you like pure existence proofs, then graph limit theory will give you several. Thank you.